Let's start a new topic, new chapter. We're getting away from the infinite series finally, and moving on to what's called parametric equations. And we're going to get into polar coordinates and a couple other things before we end up in this semester. Um, so parametric equations, this is something that may get covered in some pre-calculus classes. So you may have seen this idea before. Obviously, we're going to get into calculus things, but before we get to the calculus, we'll introduce the parametric equations. So when we talk about parametric equations, we have two functions, x and y, and x and y are both functions of a third variable, t. So we write x equals f of t and y equals g of t. And then each value of t determines a point xy. We can plot in the xy coordinate plane, and then we can trace out a curve c, which we call the parametric curve. And so you can see this curve can kind of go in any direction that it leads. Could be anything, I guess. And it doesn't necessarily have to pass the vertical line test, as we can see, because it's not a function of x. It is a function of t, and t is not on here the way x and y are. So let's see how this works when we sketch out a curve. So we have x is t squared minus 2t, and y is t plus 1. So pick values for t. So let's let t equal -2, say. Then x would be -2 squared minus 2 times -2. So we get 4 plus 4. So x would be 8. Y would be -2 plus 1. So y would be -1. So that ordered pair would be 8, -1. We pick another point for t, another value for t. So if t equals 1, for instance, we get 1 squared minus 2 times 1. So that would be -1. And then y would be 1 plus 1, which is 2. So we get the ordered pair -1, 2. And so that's how you do it. So you can pick whatever values of t you want. And then in this case, you get this curve that looks like this. All right. So let's get to the calculus of this, derivatives. So when we have f and g are differentiable functions, we want the tangent line at a point on the curve where x equals f of t and y equals g of t. Y is also a differentiable function of x. Then the chain rule gives us this, dy dt equals dy dx times dx dt, something we learned in Calculus 1. So if we solve this for dy dx, we end up with dy dx equals dy over dt over dx over dt. So if we want to find the derivative of y with respect to x, this is how we can do it. So let's find the equation of this tangent line. Now this is something we did a lot in Calculus 1. So the steps are the same. It's just a matter of getting this derivative in kind of a different way than maybe you have before. So what do we need to get the tangent line? We need the derivative, and we need a point. So we want it at the point where t equals -1. So the point on the tangent line we're going to plug in -1 for both and for x and for t in the x function and t in the y function. So we end up with 2 for x, and we end up with -2 for y. So the point on the tangent line is 2, -2. Now we need the slope, so we need to take the derivatives of x and y. So we get 4t cubed plus 1, and then y prime, no, not plus 1, just 4t cubed. And then y prime is 3t cubed, 3t squared plus 1. Then let's plug in the -1. So x prime of -1 will be -4. Y prime of -1 will be 4. So then dy dx will be 4 over negative 4, which is negative 1. So our slope is negative 1. Our point is 2, 2. So here is our tangent slope. So now let's put this in the equation of a line. So we have y minus negative 2, so y plus 2 equals the slope times x minus the x coordinate. So y plus 2 equals negative x plus 2, so that means that y equals negative x. And there is our tangent line to this curve at t equals negative 1. All right, so that brings us to area and integration. So if we have a parametric curve where t goes from alpha to beta, we can write the area. We'll write it in terms of x and y first. So the way we usually write this, we have usually f of x dx. We'll write this y dx. Y is a function of x. And so y dx. And if we want to write this as parametric function, and so y is g of t, and dx is the derivative of x, which with respect to t, so that would be f prime of t dt. And so there is our integration formula. So let's see how this works with x equals 8 sine t and y equals sine t cosine t. So we need to find, so we don't need to find y prime, we do need to find x prime. So x prime is 8 cosine t. And so our area will go from 0 to pi over 2. Y is sine t cosine t. And then f prime of t dt would be 8 cosine t dt. So here we have our y, so y dx, and here we have our dx. So now let's see what we can do with this. Let's kind of simplify this. So we have 8 cosine squared t sine t, and this should be something we should be able to integrate. We did this earlier in the semester. Maybe use substitution. So u equals cosine t, du equals negative sine t dt. And then let's change our limits of integration. So if t is pi over 2, that means that u is going to be 0. And if t is 0, then y, or u, is going to be cosine of 0, which is 1. So this goes from 1 to 0. 8, actually negative 8, u squared du. So we have our u here, u squared, and then sine t dt would be negative du. So that's where the negative comes in. So then we get negative 8 thirds u cubed, evaluated from 1 to 0. We plug in our limits of integration and we get 8 thirds for our area. So kind of new stuff with parametric curves, but nothing too hard as far as the calculus goes. It's kind of just getting used to working with these new types of equations.